All right, let's get started. Welcome to the session on the power and peril of parallel streams. My name is Venkat Subramaniam. We're going to talk about some of the beautiful things we can do with parallel streams. What are some of the things we should keep in mind when we start using parallel streams and such things. So let's get started. Let's talk about programming concurrency. Programming concurrency is incredibly a very difficult thing to do. A lot of us, including myself, have started programming concurrency without fully understanding the Java memory model. And it turns out, if we don't understand the Java memory model, it's incredibly hard to get it right. One of the, probably the most scariest book ever written in Java is Programming Concurrency by Brian Getz. And before I read that book, I used to think that you cannot get concurrency correct at all. And after I read the book, I am thoroughly convinced now you cannot get concurrency correct anymore. It is that complex, actually, in all honesty, because it's just that way too many things could potentially go wrong. Well, it turns out that there are actually two different ways that we approach concurrency. One of them is what we call as a divide and conquer problem. So you have a problem, you take it and you divide into two parts maybe, and then you take these two small parts and you make a decision whether you want to solve that smaller part or you want to go ahead and divide it further, and you can keep going in sequence through this. The other, of course, is what we normally call as parallel arrays. So you have a collection of data and you want to execute those collection of data in parallel. Well, the parallel streams really fit into the second nature much more appropriately than the first one. While you can try to use parallel streams to really do divide and conquer, it is not that convenient or really built to easily do this. It's really intended for the parallel arrays problem. When you have a collection of data, you can easily throw them into parallel execution very nicely. That's where you get this really into. So where does this parallel stream really fit in? Well, you have a collection of data and you want to perform some operations and you want to really speed up the computation and you want to do that in parallel. Well, let's take a look at how we could actually do this. A very simple example we'll start with right here. Let's say we have a collection of numbers. In this case, let's just say 1 through 6 for a minute. And I want to perform a very, very trivial transformation. I'm going to keep it extremely simple so we don't have to break our head trying to understand what the code is actually doing. So in this case, I'm going to simply perform a map operation where, given an element, I'm going to simply call a transform on the element. And then, of course, after that, I'm going to simply print out the element given to us. So in this case, of course, I'm going to just print it out as system.out, let's say println, and ask it to print it. Well, we need the transform method. Again, I'm going to keep the transform method extremely simple, so it's very obvious what we are actually doing right here. So I'm going to say transform is going to take a number, let's say, and all that it does is simply returns the given number. So not a big deal at all, as you can see. So we printed the numbers 1 through 6 right here. But of course, this is running in sequence as we would expect. So I'm going to put a little sleep here of, let's say, a 1 second interval. And of course, sleep is just a method I'm going to write here. And this is going to just give us that many milliseconds to sleep. So what's going to happen in this code when we run this little example? Let's just go ahead and run this from the command prompt just to take a look at it. And as you would expect, it's taking about a second to run each one of those values, and it's printing those values one at a time sequentially. So that's a pretty simple, trivial example, as you can see. But I want to run this, let's say, faster. Imagine the transform is actually a real computation, not a dummy thing that's just returning a number. Maybe it's trying to figure out the meaning of life. It's going to take a lot of time. And so if you're going to pass these values and get the results from it, well, how do you really perform these operations? Maybe you want to speed it up by running that in parallel. So to make this really parallel, there are really two approaches you can actually take. And one of them is to turn the stream into a parallel stream just by using the word parallel stream. And of course, in this case, it's going to run in parallel right off the bat. Let's see if it really does. Go ahead and run this and you can see, boom, it actually printed the result right there in one shot after the second. So that's running in parallel. When would you use this approach? Well, if you are the source of the stream, it makes sense to use the parallel stream at the source because you have the ability to create a stream, and while creating it, you can say whether your intention is to run it sequential or run it to parallel. But what if you're not the source of the stream? Imagine you are really receiving a stream on your hand and you are the intermediary somewhere in between. Then what do? Well, the good news is you can do a dot parallel right here, and you can convert a stream into a parallel stream by doing this as well, as you can see right here. So this is yet another approach for you to be in between in the middle of the pipeline and say that you would like to really convert this to a parallel stream, and you can do this. Again, let's make sure that's actually working. So go back and run the code, and you can see it ran it really in one shot. Before we go further, one small peril you have to be very, very careful about, because it's a bit misleading when you're, kind of not really thinking about what's really happening. For example, you may wonder if there is a parallel call, maybe there should be a sequential call as well, and it turns out there is a sequential call that you could actually use. Let's remove the parallel just for a minute from here. It is a sequential stream. You already know it. You just said sequential. Well, is it running sequential? Well, sure enough, you can see that it's running sequential. I won't wait for it. So the temptation here is, this is so awesome. We could take this map and run it in parallel and do the for each sequentially. Well, not quite. So the last one actually wins. So in this example, this entire pipeline is going to run sequentially, even though we said parallel in the beginning. So you have to be very careful about it. In the case of parallel streams, or in the case of streams, you don't have an ability to flip back and forth between segments of the pipeline to run parallel versus sequential. This is purely either fully parallel or fully sequential. So in this example, notice I did say parallel in the beginning, but I'm saying sequential right after that in the middle. But when I run the code, notice though, in this example, it is still running entirely sequentially. The map is not running in parallel, and that is because this actually influences the entire pipeline. So from the beginning, not just from that point onwards. So we have to be very careful how we use the parallel versus sequential. But also begs the question, if it's so really easy to create a parallel stream, then why don't they really make everything parallel? That's a question I've been asked several times by developers. My gosh, look at that. You can just say parallel stream and make it run parallel. If it is so easy, why didn't they just do it for everything? Well, I call this a master switch. And the reason I call it a master switch is they made it so easy up to the point where they could have almost done it, but they didn't do it, and then gave you the switch and uttered one word at you, and that word is called think. So they want you to think about this before you turn on that switch, because turning on the switch is really easy, but the consequences could be really devastating if you're not very careful about it. So what are some of the things we have to be careful about? We'll take a look at it. So in this case, I want to know what threads are running our little code. So to understand what threads are running our code, let's go ahead and run this little code again sequentially, if you will. But I'm going to observe the thread that's running this. So I'll come in here and output, let's say in this case, we'll say transform. And then, of course, we will say the number we are transforming, plus we will output, let's say thread.current thread, and we can take a look at the thread that's executing this particular piece of code. And of course, when I go back and run this little code, as you would imagine, it is telling you that every single piece of that code is being executed by the main thread. There's no surprise there at all, as you can see. I'm going to suppress this particular output so we don't have to really look at it. So given the element, I'm going to simply say don't do anything with it, so we can just see the output of transform alone a little bit more clearly at this point. So we can see that the whole thing is running in the main thread. That's no surprise at all. But on the other hand, of course, what if I'm going to go back over here and execute this, let's say, in parallel? So if I were to then do a dot parallel, whether you do it dot parallel or you create a parallel stream at the source, really doesn't matter. As you would expect, when I go back and run this code, you notice that all of them are going to run concurrently, but in what thread? They're running in the fork join pool thread, as you can see. But notice that almost all of them ran in fork join pool, but on the other hand, the first one did run in main. Main is a really nice thread. It doesn't sit there and say, you all do the work while I watch you. It participates in that as well. In fact, that is one of the reasons why the fork join pool usually has one less thread than the number of cores, because main is actually a participant in that as well. But you are kind of looking at it like, really, why are we so strict about that count? We'll talk about that a little bit later. So let's talk about the order of execution. I want to execute these things and print the result. So going back to this example right here, let's go ahead and suppress this output for a minute. Let's get back to this and say I want to really print out the result. So system.out, let's say println, and then I'm going to print the results out of this right here. Well, obviously, in this case, when I go ahead and run this sequentially, it is going to really preserve the order. Well, keep in mind, not all streams have ordering. Some streams have ordering, some streams don't have ordering. How do you know if a stream has ordering or not? Well, one way to know is what is the source of your stream. If you started with a list, we know list is ordered, we know a set is not ordered, so the source of a stream may decide whether a stream is ordered or not. You can also call methods in between that might impose ordering on a stream, for example. So it depends on whether a stream is ordered or not. In this example, the stream is of course ordered, we know that. So when I go back and run this little code, you can see from the output that we get, it's sequential of course, but it's in the same order as you would expect. So the ordering is preserved because we have ordered collection 1 through 6. But the question is, what's going to happen when we turn it into parallel though? Because it's going to run in parallel, there is no guarantee of ordering. So in this case, as you can see, it gave us completely arbitrary order. If you run it again, 5, 4, 3, 1, it's 2, 1, 3, 5. Well, here's the good news. You got the result really fast. But the bad news is the endpoint is really not sequential. Imagine you're creating a report. It doesn't help the customer tell them, good news, I got it really done fast. Bad news, it's all jumbled up, go figure out. That's not going to invite a good customer. So how do you really manage this? Well, here's an idea. There are certain methods that will impose ordering on the execution. So in this case, I'm going to say for each ordered, and before run this, let's really talk about it. I am not suggesting by any stretch of imagination that these are running sequentially. No, actually not. They're actually running concurrently. However, the very last step says, I will not run until the guy before me has actually executed. So it imposes ordering. Ordering doesn't mean sequential. They do run concurrently, but it imposes an ordering at that particular point. The point really here important is that the map actually runs in parallel, as we will see in just a minute. So if I go back and run this little code example right now, you will notice that they are all running, but notice no matter how many times I run this, the result is completely ordered even though it's running concurrently, and that is really good news that it has an order imposement. Well, let's make sure that actually that's true. So if I go back and turn on that print statement on the map method and run this again, you will notice that they are running in actually different order. Notice that from the output 1, 4, 6, 2, but from the output you have 1, 2, 3. So the ordering is in the very last step, not in the execution of the map itself. They did run concurrently, and they all kind of come to a grinding halt and say, well, I won't go until this guy before me goes, and then that's when they are really being in sequence, if you will. So that is really a good news that you can have ordering. There are certain methods that will impose that kind of ordering for you if you were to use them. So that's, you can kind of have the best of both worlds in that situation. But we control the ordering, but the question really is, how do things really work when it comes to applying parallel? You already saw this example. I was able to use map in parallel. Similarly, the filter will work in parallel. But then we kind of wonder, will things like reduce work in parallel as well? Well, to understand this, let's go back to this example. Let's do this sequentially one more time. But this time around, I'm going to go ahead and call the output right here. But in this case, I will ask the very last step to perform a reduce operation. And we'll say 0, comma, total. In this case, let's go ahead and say total comma element, and we will call a method called add, which takes the total comma element and returns the result. Well, this add method is going to take two numbers and add them. Before I talk about this in particular, let's understand what reduce is actually doing. Let's say I want to total the age of everyone in this room, starting with him. He's not smiling at this point. I'm not going to ask you real age. So let's say we'll start with him. So what am I going to do? I'm going to give him a 0 as a value. That's age of everyone to his right. He takes his own age, adds 0 to it, passes to the next gentleman. He takes the value given to him, adds his own age, passes to the next gentleman. And then as this data passes through the room, the value that I get out of the last person in the room either is the total age of everyone in the room or an overflow, depending on how old we are in this room. But the point really is that we are going to have this sequentially. The value is going to trickle through this room, and we get the result over there. That's kind of what a reduce is doing. It collects the results and brings us back to one single value. But I'm curious to look at the add itself. Let's go ahead and once again remove this printout from the map method. But in this case, I'm going to create a method which is the add method, which takes the value 1 and int value 2. And all I'm going to do is output, let's go ahead and say add plus. In this case, we'll output the value 1, and then we will output the, let's say, the value 2. And then finally, we will go ahead and output, let's say, the thread information as well. So thread dot, let's say, current thread, and print it. Well, if we do this, it's sequential execution at this point. We start with the value of 0, like I said. He's going to take his own age and add to 0 and then pass it down. So as a result, what you're going to see in here is that basically when you run this code, you can see that in this case, well, actually accomplish an error, but we'll fix it. So in this case, of course, as you can see, it is going to sequentially run through each one of these and get you the result out of this eventually. So let's go ahead and fix the error right here. It would be nice to return the result here, isn't it? So let's say return, in this case, value 1 plus value 2, which is the result of the add function. Let's go ahead and try this one more. So in this case, you can see that the add is being called in the main thread. The value 0 plus 1, and then the result of that is 1 comes down here, 1 plus 2. The result of that is 3 comes down here, 3 plus 3, the result of that is 6. And then you can see that it goes through sequentially. But the question is, does it make sense to do this in parallel? Let's go back to the example we just talked about just a second ago. I'm going to give him a 0 and say, let's total everybody's age in this room sequentially. But then I quickly realize, gosh, I don't have to really do this. I am going to give every person on the left corner, my left, in this row, a value of 0. And similarly, everyone in this corner, I'm going to give a 0 and say, why don't you all, every row, total your age concurrent? Well, at the end of that first step, I'm going to have several, as many rows as we have in this room. I'm going to have that many totals on one side and that many on the other side. And I can then say, hey, the people on this row total the values this way, and people on this column total the value this way. In the second step, I'll have two values. I can put them together and get the value immediately. In other words, we could do a divide and conquer of this. I don't have to really do this sequentially. Case in point, in this case, if I go back here and try to run this in parallel, you will notice right away when I run this code, you can see that it is actually running that all in parallel. As you can see, all that add is being called in multiple threads, and you probably notice there are more calls to add than before. As I said in the case, I'm going to call add on different groups of people and then collect it together as well. And the result is news. Whether you ran it sequential or concurrent, the result is still 21. Hey, that is awesome, isn't it? Because I could run this code sequentially and the result is 21, and I can run the code concurrently and the result is still 21. That is one rule of parallelism. You cannot get a result faster and say it's okay if it is not correct, right? It doesn't make any sense. The result has to be still correct as well when you do this. So, but you have to be very careful though. The value that you provide here is not an initial value. We've got to be very, very careful about it. It is actually an identity value, not an initial value. For example, for addition, 0 is the identity value. For multiplication, 1 is an identity value. This is important to keep in mind because let's say I'm interested in totaling my own age to the age of everyone in this room. So I'm going to say 20, right? So you don't believe that? Okay. So I'm going to start with that number. Well, 20 plus 21 is the result we really want in the very end. So when I run this, of course, you can see the result should be a 41 because the initial result was 21, and we see that it's actually 41. But we are in real trouble now because I did not give an identity value. 20 is not an identity value. I mistook it as an initial value. The result is catastrophic because when I run this code this time, the final is no longer 41, it is 141. Don't bet on it. It could be completely different the next time because it is feeding all these parallel values with the value of 20, which really doesn't make any sense. So that is something we have to be very careful again when we use parallel. We really have to, it's no substitute for knowing what we do in general, but especially with parallel, that's very important. There's no point in getting a really wrong result really fast. If you really want to get a really fast, if you really want to get a result really fast, and you don't care about whether it's right or not, you really want to go back and program in C++, isn't it? So absolutely, this is not the reason to do it. So we really want to make sure that we get the result correctly as well, not just faster in this particular case. So when we go back and run this, if, of course, in this case, the result is still going to be the same because I'm providing an identity value. Well, then the question is, if I really want to add my age, I do, well, sure, that's not a big deal because I can come back here and add it at the very end of this particular call. Of course, in this case, correct. Something to keep in mind, what you're sending in as an initial value makes a huge difference. But that begs the question, we've been looking at these threads. What do these threads really do? What do they really use? We really want to understand it. So how many threads do we get without doing any single work? And to understand this, let's look at a little bit of an output right here. Let's get back to this little map function. And then we'll say for each, in this case, given an element, I just want to simply suppress the output. Let's go back to the map method, transform method, and print that result out. So this will give us a little bit of an idea how many threads are going to run for us. Now when I go back here, let's go ahead and take values 1 through 7, let's say 8, 9, and 10. But I'm going to repeat this one more time in here. Let's say I have the values just repeated. So I have these values, even if we want to really say, let's say this is 11 and 12 and 13, I can have these little values being provided so that we can see how many threads are going to run concurrently. Well, it turns out the way this actually works is that by default, you get as many threads as the number of cores on your machine. So I want to know how many cores I have on my machine. So let's go ahead and remove this just momentarily. And I'm going to go back here and say output runtime dot runtime. So in this case, let's say runtime. And what am I going to ask for in this case? I don't remember this method right now, but available processors, right? So I want to know how many processors are available, and it tells me there are 8 processors available on my machine. So that is a way for you to find out how many cores are available. It is a blatant false information, by the way. It's a lie. I don't have 8 cores on my machine, but that's what it tells me. So in this case, of course, it tells me that I have 8 cores. I have actually 4, but it just wants to count it as 8. Well, that's fine, but it's going to give me a total of 8 threads. Well, remember, main is part of that as well. So the common fork join pool contains a total of 7 threads when my machine has 8 cores. How do I know this? Well, here's a little example. We could simply go ahead and say over here, fork join pool dot common pool. That's a way you can get access to the common pool, and then you can ask for the details from it. Obviously, to use this, I need the Java util concurrent, so I'm going to bring that in here. So here is concurrent, and what am I going to do at this point? So notice I'm going to ask him for details about the common pool. When I go back and run this little code, it tells me I have 8 cores, but notice this right here. It says parallelism is 7. Well, that's because 7 plus 1 is 8, which is the total number of cores on my machine, main being the other participant of this particular club. So that is basically what we are seeing here. The fork join pool is being used. Now here's a way to think about it. Because of the nature in which these things work this way, how is this going to be scheduled across those different threads? As you would imagine, I have 20 elements on my hand. I'm going to schedule those 20 elements over 8 cores on my machine. So how many batches are we looking at approximately, give or take? 3 batches. So 8, 16, and the remaining to achieve the 20. We can actually see this in motion here. Let's go ahead and run this. I'm in burst of call. Here's the first of the call. Well, actually, if it compiles, that is. So let's go ahead and remove this output right here and try this again. So we're going to see a first burst of the call right here. So let's see if that's true. So here is burst 1, burst 2, burst 3, done. So that's in 3 bursts, as you can see, the output came through. And the reason for 3 bursts, in fact, a little bit easier if I remove the thread details for you. So pardon me here, while I make it a little bit more easier to see with a little concise output. So here we go. That's burst 1, burst 2, burst 3, and done. So that's obviously scheduling across those 8 different threads that are available on my system. But that brings up the question, why so careful about default threads? Why can't we just go wild with it? We'll see why there is a reason in just a second. So when you're doing parallel streams, you have to be very careful. They didn't select number of cores equal to number of threads by default arbitrarily. They are very, very clever. They said, if anything were to go wrong, they want you to take the blame, not them, right? Which is only what I would do if I was designing libraries. I don't want to be blamed for decisions I make. I want to be very safe in decisions I make. So the safest decision I can make is to give you as many threads as a number of cores. But that begs the question, why in the world is that safe? Well, I'm going to give you a really silly example. Imagine there are monks, and you know how monks are the most polite people, right? Imagine there are 4 monks and there are 2 treadmills. So the 4 decide to go to a gym. So they go to the gym and 2 monks get on the treadmill. And you know how monks are very polite. They get on the treadmill and they look down and say, oh my dear God, you both are waiting. How rude of me to be on the treadmill. And they immediately get down from the treadmill. The other 2 monks get on the treadmill and what do? They say, how rude of me when you are waiting there, I am on the treadmill, and the monks never exercise. This is why it's good to be rude in life sometimes, isn't it? No, just kidding. But the point really is, this is exactly what threads are going to do. If your threads are computation intensive, they behave that like those monks. They're going to get on the CPU. In this case, the ones below are the ones pulling it down. So it's kind of a little controversial in this case. But the threads waiting say, hey, you get off, it's my turn. And the threads running on the CPU say, but I have work to do. I don't care, it's my turn, get off the CPU. So they yield the CPU only for these to get on. And guess what the ones that got off do? They turn around and say, you get off now. And they're going to trash each other. We're going to lose performance if we're not careful. So the moral of the story is this. So the number of threads that you always want to give is less than or equal to, and then you can do a little quick formula. You can say on the numerator is the number of cores on your machine. We'll start with this. And then 1 minus, well, then I'm going to say this is called the blocking factor. So let's say, what is a blocking factor? So if I am the blocking factor is 0 less than or equal to the blocking factor less than 1. If I'm a computation intensive thread, then what happens? If I'm a computation intensive thread, I'm running and running and running. I have no opportunity to take a break. I have nothing to sleep for. Well, my blocking factor is 0. If I'm an I/O intensive thread, I want to write to a database. I want to read from a database. I want to make a call to a remote system. I want to write to a log file. I want to open files. And every one of these opportunities is when I'm going to say, CPU, you take it easy. I'm waiting on this file to kick in and bring the data to me. And what is the CPU going to do? The CPU is like, gosh, I don't have any work to do. You are sleeping at the wheel right now. You're going to go get the data. Well, you might as well work on another thread that requires processing when I don't have anything to do. So if you have an I/O thread, task, you can have more threads using your CPU, more tasks using your CPU at that point. So if I have a task which is sleeping for, let's say, in this case, let's work the formula. I'm a computation intensive thread, which means the blocking factor is equal to 0, isn't it? Then the number of threads I want to really create is less than or equal to number of core, because 1 minus 0 is 1 in the denominator. But if I'm an I/O intensive, let's say blocking factor of, let's say 0.5, then the number of threads that you can provide me is less than or equal to 2 times the number of cores in reality. If I'm sleeping most of the time, you can give me more cores, assuming, of course, that there is enough work to do, right? And of course, if the blocking factor is 1, that's a deadlock. You don't want to go there. So absolutely, you can give more threads if I am I/O intensive, fewer threads if I am computation intensive. Now you know why they chose the number of threads default is equal to number of cores, because that's a very safe bet, because they don't know what you're doing. They cannot predict what you're doing. So the safest bet is to say, hey, you are computation intensive. But what if I am not? Well, then you can vary the number of threads you want to use. Well, here's the formula we just looked at to decide the number of threads, but how do you really configure the number of threads that you want to use in your application? This is a dangerous setting, be careful using it, but this setting simply says -d at the JVM level, java.util.concurrent.forkjoinpool.common.parallelism. I love this property. Finally, something longer than my name. So as you can see here, you can specify this property and ask it to use this right here. So how do I use this? I'm a little lazy person. I'm not going to really type this all manually. So I'm going to show you the example by using little script where I'm going to use this thread. So here is a run config I have written for myself where that is setting that property. As you can see, the run config is doing it, so I don't have to manually mess with this. If I run the run method just now, as we saw, it's using the default number of threads. That's burst 1, burst 2, burst 3, as you can see. But if I do run config, on the other hand, and give it 100 threads, that's burst 1 and I'm done, as you can see, because it gave us 100 threads to run, not just one set of 8 threads. Be very careful using this feature because it changes the settings on your entire JVM, not something you want to do so quickly without thinking. Also, if you're using, one other thing I've heard from clients quite often is they'd be using a third-party container. Don't mess with this when you're dealing with third-party containers. Third-party containers are mostly intended so they can take away the threading from us. So this is kind of going contrary to that. Be careful about it. You can also configure this programmatically as well. How do you change this programmatically? If you want to change this programmatically, what you can do in here is you can create your own fork join pool. So fork join pool, let's say over here, pool is equal to new fork join pool of 50, let's say. And then I'm going to say pool dot shutdown. This is one of my things usually. I want to shut it down as soon as I create it. And this is going to require that you handle exception. We'll come back to that in just a minute. And then I'm going to say over here, a pool dot await termination, and then I'm going to say, let's say 10 comma time unit dot, let's say, seconds. So I'm going to give it 10 seconds for it to finish up all this. Now within this, what I could do is I could say pool dot submit, and within the submit I could simply go ahead and say that I want to perform that operation right there in parallel, of course. But notice the call to this parallel comes from within this right here. And as a result, because I'm calling this in a fork join pool, this is going to run in the pool which is native to that particular call, and it's going to do that. Of course, this won't work at the moment. It complains that I have to deal with interrupted exception. This is a game we always play with Java, right? You write some code and Java says you will handle the exception, and you as a programmer show who's in power by putting throws exception, right? So this is very awesome. So basically in this case, you kind of say, all right, I'm dealing with it. So in this case, what's a thread? Notice it's no longer the common pool. It's a fork join pool we just created right off here. That's what we are really doing at this point. So that is one way you can programmatically control. What is nice about this is you can have different computations executing at any given time, and you can tailor the needs of those computations separately without one global setting in your application. So that can work really well for you depending on what you're trying to do. Well, let's go a little further to talk about some ways in which we should really be very careful again, because we can really mess up things if we are not very careful. So let's switch gears to a little bit of a slightly different problem here. I want to be able to run things faster, but when parallel may not be really a good thing to do. So to understand this, I mentioned that you have to be very careful with the number of threads. To illustrate this point, allow me to bring in a little code here, and I'm going to go ahead and bring in a concurrent example right here. And in this case, I'll go ahead and say in this, let's say this is computation, that's what I want to call as. And I'm going to bring in this little computation code, and what I'm doing is a pure example, trivial example. When you call compute, it opens up 2 for loops and performs square root operation on it. And then of course, out here, I total the sum, find the sum of all the square root of all those values. In short, it's a computation intensive operation. I'm just throwing this through these loops and running them in sequence, as you can see right here. This is pretty much a sequential code. How much time is it going to run to do this work? So I'm going to just run the sequential code, and I don't know, it's going to take maybe a few seconds to run. I don't want it to be too long. And it's going to come back and give us a result in the very end of this. So you can see that it's actually taking a little bit time to execute it. But I want to make this faster. I want to run this faster. I forgot to say time on this. I apologize. So I'm going to run this now, but I don't want to wait for it. But when it is done, it's going to tell us how much time it's going to take. In the meantime, let's run this in parallel. So I'm going to go ahead and say dot parallel right here. And what is it going to do now? It's going to run in parallel, sure, but how many threads? As many threads as the number of cores on my machine, because I'm using the default settings. So we are hoping this will be faster than the sequential run, which actually took about 13 seconds. That's what it says, right? About 13, 14 seconds. Just keep that in mind. So I want to go ahead and run this in parallel now and see how much time it's going to take. So now that it's parallel, multiple threads are going to run this. Hey, notice that we finished in about 3 seconds instead of 13 seconds. I would say that's pretty decent because we made it faster. But now I'm going to be that person who is jealous. I'm sorry, I want more of this. So I'm going to run this config with 1,000 threads. Why not? I have the power to create threads, so I'm going to go ahead and create those threads after all. We went from 3 seconds, and what does it say in this case? Of course, I forgot to do the time again, so we'll do a time on this. And what does it take to run this after 3 seconds that it took earlier? It took about 4 seconds, as you can see. So it actually did not take less time. It, in this case, actually took more time. I've actually worked on projects where a sequential code takes an hour to run. The parallel code did not finish even after we came back from lunch. And we really had a very long lunch, actually. So the point really is you could really mess up things if you're not careful with it. So there's a reason for controlling that. One other thing I want to quickly mention here is we really have to understand that certain things may not go in our favor with parallel. So to understand this, let's take a slightly different example. But before I go into the example, let's kind of talk a little broadly. There is a couple of things you need to ask before you turn your code into parallel. The first question is, do you have a lot of data to really process? Maybe parallel is an answer in that case. Do you have a lot of work to do? Maybe parallel is an answer in that case. Imagine you have 2 children at your home and you're running out of sugar. So you yell out saying, hey, I'm running out of sugar, go get some sugar from the neighbor. One kid goes out to get into the bicycle so he or she can ride to the neighbor. The other kid jumps the fence. Do you know which kid is going to get you the sugar really quickly? The one that jumps the fence, obviously. Because the neighbor is just the neighbor, right across from the fence. You don't have to go through a lot of effort to get there. Jumping the fence is quick. On the other hand, you say, I really need a bag of rice. Go to the store 5 kilometers away and get it. Well, one kid jumps the fence, the other one takes a bicycle. The one that jumps the fence is probably going to end up in jail. So you don't want that kind of behavior at that point. So you really have to ask the question, how much distance am I covering? How much data am I processing? What is the intensity of the task? Do always benchmarking. Oh, by the way, I never trust benchmark anybody else creates. It's got to be something I do for my project with the relevant information on my teams. And that's one of the reasons why I never trust anybody's benchmark, including my own, when I switch between projects, that is. So you have to really try it out and see if it makes sense. But having said that, let me give you one other example I want to quickly point out here. I want to take an example here of, let's say, working with a collection of people. So in this example, what I want to do here is, I want to take this create people, let's say create people list over here, and I got a bunch of people on my hand with different names, different gender, and different age. But what I want to do here is the following. I want to say in here, given the people collection, so we'll say create people, I want to say dot stream, then I'll say filter. Given a person, get me the person dot, let's say get age is greater than 25. Well, I want somebody who is older than 25. Then I'll say filter person, and I will say person dot get gender, and I'll say in this case gender dot female. And then I will say dot map, given a person, give me the person dot get name of the person, if you will. And then finally what I'm going to do here is to say, maybe convert it to an uppercase. So let's go ahead and say string to uppercase. So in this case, of course, what I have done is, I've taken the first person older than 25, who is a female, got the name and transformed to first uppercase, but then I say in the end, find first. And I'm wondering, who am I going to find really? And then of course, or else will say, no one found. So I want to just print this and see what the output looks like in this particular case. So let's output this right here and see what we get out of this. So in this example, of course, I'm going to run this little code, and it says Paula. Well, sure, it's Paula, because if you go through the list, it's an ordered collection, and Sarah are not older than 25, Bob is not, Ta-da, Paula is the first person older than 25, and he's also female, so we got that. But the question is, effort did we put in? I'll come back to that in just a minute. But let's go back and run this code several times just real quick here. Let's go ahead and say run.sh just once. It says Paula, but I want to run this many times. So here we go, and I'm going to keep running this, several times. So I could keep going in a number of times right here, and I say run this all. And it's going to be repeatedly Paula, isn't it? Doesn't matter how many times I run. I know running this is not a proof of it, but just trust me. It's going to be the same as many times as you run it. But on the other hand, there is also a function called find any. What does find any say? I don't care who it is, just find one of them. Well, find any will give us one of them if it's available. So in this case, when I go back and run this, what am I going to get? It turns out it's Paula too, not fair. Why? Because it's sequentially executing. And because it's sequential, the first one is always the any as well, right? Okay, that's kind of easy to see. But let's get back code now, put it back in find first again, but in this case, I'm going to turn this into dot parallel. Well, what's going to happen now? Remember, this is an ordered collection. And remember, we talked about certain methods being ordered in the past. Remember that? We talked about for each ordered. Well, find first is one of those guys. It doesn't have the name ordered in it, but it's going to impose ordering in the very end. So you're going to do this in parallel. Awesome. But unfortunately, though, you're going to do this in parallel, which is great. But what are you going to get? You're going to get Paula all the time. You better do, right? Because you want the first one. The ordering is important to you. Let's see if that's true. Let's go ahead and run this and see it's Paula every single time. Again, that's not a proof. Just because I run it 70 times, it doesn't mean it's correct. Again, trust me on that. Research on this. But what if I turn this into a find any on the other hand and run this code now? Well, this time notice it is still Paula, but I'm hoping it'll be different sometime. Okay, it's not in my favor. This is the peril of a demo, isn't it? But hopefully at some point you will run this enough number of times, and okay. So again, trust me on this one too, right? So what is it? Oh, is Paul the only answer here, you're saying? Well, okay, there are no other people. I blame it on you. Okay, thank you. So let's make it as, let's say, oh, Jill, where is Jill? Jill, my friend. Let's just make Jill older. Okay, so there we go. So, all right, try this one more time, this time. I didn't even notice it, but good catch. There you go. Thank you. All right, yeah, thank you for debugging that. My faith in pair programming was just restored. All right, so right there we got the result, the case in point, right? But of course, if I go back to this and say, this is going to be find first, on the other hand, you will, it better be Paula each time this time, right? So in this case, of course, it'll be the exact same value every single time. You with me so far? But there is one thing I love about streams, and that is laziness. Well, let's talk about that real quick. Let's go ahead and remove this parallel for a minute. Let's just do find first, if you will. And I want to know who all I'm going to talk to. Here's our Jill, who just got older. But we have Paula, who is older than 25. But who am I going to talk to repeatedly? If I go to the person class right here, in the get age, I'm going to print out right here. I'm going to say name, get age, and then plus name. And then, of course, I'm also going to, name. And then I'm also going to output, in this case, I wanted the gender as well, didn't I? So I'm going to go ahead and ask for that to be printed right here too. So I'll go ahead and say this is going to be get gender and print that information. Okay, that's great so far. I'm doing this sequentially, as you can see in here. So I'm going to go ahead and run this code. And the beauty, I'm just going to do it once. So I'm going to run this code in sequence. And as you would expect, it did not touch anyone after Paula. Makes sense, right? Because it's lazy. It says, I don't need to run this fast. I'm going to just process Sarah, Bob, Paula. Ta-da, I got my result. I never have to talk to anyone besides Paula. So it never touches Paul, Jack, and Jill. On the other hand, I'm going to go in and say a dot parallel right now. Now what's it going to do? It says, whoa, look at this. Let's get to business. We got data in front of us to do work. And it's going to be on fire, isn't it? And as a result, what is the result going to be in the very end? still parallel, but it's not going to be lazy like the way we thought it is, and notice a lot more work being done. Let me summarize this in a slightly different example. Let's say I was just hanging around here, and as I was going around, what's your name, sir? Thomas? Let's say I left my phone next to Thomas, right? So here's what I could do. I could say, excuse me, is my phone next to you? He says, no. Excuse me, my phone next to you? He says, no. Is my phone next to you? Oh, thank you. He said, yes. And so how much effort did I take? 3 units. How much time did I take? 3 units of time. And I got my phone after that. But that required a little bit more effort. Here's something else I could do, right? I could just say into this room saying, folks, do me a favor, please. Is my phone next to you? How much time will it take for me to get the result? 1 unit of time. How many people did I disturb? Hundreds of people. So the good news, I got the result faster. The bad news, I bothered everyone. Good news, I don't care. So that is the beauty of this. So that is the moral here, right? The moral here is, I don't mind throwing more hardware at this problem with the hope of getting the result faster. Hope that was useful. Thank you.